postdoctoral fellow at NIKHEF and also at the University of Utrecht. And he's a member of the LIGO scientific collaboration, where I don't want to be wrong, but I mean, you chair the lensing working group.
Yep.
So Otto obtained his PhD in 2019 at the Chinese University of Hong Kong, and actually he will be back this year in fall as a research assistant professor. So Otto works in several aspects of gravitational wave astronomy, including searches for signatures of gravitational wave lensing that he will talk about today, but also searches for ultralight bosons and dark matter. So he's going to talk about the search for lensing signatures in the first half of LIGO-Virgo third observing run, work that basically he led within the LIGO and Virgo collaborations. So thank you very much, Otto, for taking the time to talk to us. And the floor is yours.
Yeah, no, thanks a lot. And yeah, before I begin, thanks a lot for setting up the seminar and for inviting me. I'm very happy to be here. And yeah, so as Juan mentioned, I'll be focusing today on the latest LIGO-Virgo search results. So there was a paper a couple of weeks ago. There was. I think I can hear some background.
Yeah, we're hearing Javier, I think.
Sorry.
Oh, yeah, no problem.
Sorry for that.
Yeah. So I'll be talking about basically gravitational wave lensing. Now, Juan mentioned that the audience tends to be quite broad, and so not everyone is necessarily familiar with what gravitational wave lensing is or what gravitational lensing is. And so I'll start off the presentation kind of introducing some basic concepts and maybe motivating a little bit on why I think that gravitational lensing is a worthwhile topic to investigate. And then we can move on to the actual studies of some of the details. And so the beginning is going to be very kind of friendly, audience friendly. The latter part will involve a little bit more technical details, but hopefully everyone can follow at least the first part and then hopefully also the second part, but this is going to be more kind of detail oriented. And so the way that we'll start is through gravitational lensing of light. So what you can see here are several different observations of gravitational lensing. And so the basic principle, basic principle idea behind gravitational lensing is that when light travels near massive astrophysical objects like galaxies or galaxy clusters, what happens is that the light trajectories change. So they're bent by the gravity of that object, so the space-time curvature. And because of that, gravitational lensing takes place. And so you can see several examples of gravitational lensing observations here. So as an example, this is an Einstein ring where there is a lens here, so a galaxy that has distorted the background galaxy into this Einstein ring, so ring-like structure. And that is an example of strong lensing. You can see here an example of another example of strong lensing where there is a quasar that is multiply imaged into this so-called Einstein cross. So if you look at this, it looks kind of like a cross. Here is an example of weak lensing. So essentially statistical distortions that are distorting the background light due to mass that is intervening between us and the source galaxies. And here is another example of weak lensing where astronomers have measured the mass distribution of dark matter in a bullet cluster using weak lensing measurements. And here's an example of microlensing. And so the reason that I'm starting off with gravitational lensing of light, although the topic of today is gravitational wave lensing, is that there are a lot of analogies between the two. And it's also interesting to look at a little bit about the history of gravitational lensing. So this is a field where it really started off as a very abstract theoretical idea, and it grew into an observational tool that we had some observations of gravitational lensing, and ultimately it became a fairly standard tool, I think, in the study of astronomy, astrophysics, and cosmology. And because of this reason, most people that work within astronomy, astrophysics, or cosmology, they are familiar with the concept of gravitational lensing. And they know that it has been used for several exciting discoveries, like putting constraints on dark matter, studying exoplanets, and studying the expansion of the universe, among many other things. To the point that it is essentially a very mature tool that we use on a routine basis. Now, that is gravitational lensing of light or electromagnetic waves. But when it comes to gravitational lensing of not light, but gravitational waves, the story is a little bit different. So we're at the stage where we understand the theory behind gravitational wave lensing quite well. So this is essentially, the theory is very similar to light lensing or electromagnetic lensing, and it's illustrated here. So if you have a gravitational wave source, then just like light, when the gravitational wave propagates near massive objects like a galaxy or a galaxy cluster, the trajectory changes, it gets magnified, and it arrives to us with a time delay due to having traveled a different trajectory and through a different gravitational potential. And so just like with light lensing, you can have multiple images. So you could have another gravitational wave traveling through a different trajectory, arriving to us maybe 1 week later as a repeated event. And if there are smaller microlenses here, they can also create these frequency-dependent deformations on the waveform. And so this process by which this happens is quite well understood, because the theory behind it is very similar to electromagnetic lensing. And that's, of course, great news for us, because it means that we can take many of the theoretical groundwork that has been established through decades of electromagnetic research, take it to gravitational wave lensing and apply it there. And so essentially, the theory is very similar. And because of that, there's usually this question that, okay, well, if the theory behind the two are similar, and if it's essentially the same phenomena, what is new and what is actually interesting about gravitational wave lensing? So the differences come in terms of detection methodologies. So instead of using telescope imaging, like some of the observations that we saw in the previous slide, we're not using telescope imaging to detect gravitational wave lensing, but we're using laser interferometers and waveform templates. And so the ways in which we detect gravitational wave lensing are entirely different from lensing of light. And also, the science cases are also very different because we have a very different source population. So we are observing binary black holes and gravitational wave sources as opposed to electromagnetic sources like quasars. And we're observing waves as opposed to particles. And so the science cases are very different. And so concretely, essentially what happens, or everything that happens to light lensing can happen also to gravitational waves. And so they can experience magnification, multiple images, or these sort of frequency-dependent deformations. So that is in a nutshell kind of the 2-minute intro to what gravitational lensing of gravitational waves is. But another question is, why is it interesting? So why do we care about gravitational wave lensing? And since the topic of today is the latest search results for gravitational wave lensing, it's also worthwhile to think about why is it that we're doing these sort of searches now? So why is it that gravitational wave lensing is in our opinion worthwhile to look into, and why is it worthwhile to look into right now? And the answer to that comes from the global gravitational wave detector network to some extent. So it's illustrated here. I won't go into the details of these detectors, but I'll mention that over the years, what we expect to happen is that the global gravitational wave detector network will grow in sensitivity. So this is due to the detector upgrades that will be installed and new detectors coming online. And what happens when the network becomes more sensitive is that we will gain access to new populations of binary black holes. So there are binary black hole populations that are beyond the current detector horizon that we can't access now, but we will be able to access in the future. And as this takes place, what we also expect is that we get access to new scientific avenues. And the reason that this is relevant to gravitational lensing is that gravitational wave lensing is one such potential avenue. So some of the recent forecasts that exist in the published literature, they predict strong lensing at a reasonable rate at the ground-based design sensitivity. And so this is essentially the reason why it's important for us to study gravitational wave lensing, and why it's important to do these sort of studies, and maybe why it's important to do it now as opposed to, let's say, 30 years later. Now, I do want to mention that the rates are subject to uncertainty. So there is the population of binary black holes at high redshift is not very well constrained. There are theoretical modeling that goes into it. And so because of that, the forecasts are also subject to some uncertainty. But what I want to emphasize is that it is not unreasonable to think that we would see gravitational wave lensing within the ground-based gravitational wave detectors. And so that is one of the reasons why that motivates some of these studies. Another reason is that if we were to realize gravitational wave lensing in practice, then this would be the first time that we're seeing a new source population. So all of the current observations of gravitational lensing come from electromagnetic sources. If we were to see gravitational wave sources, then this would be an entirely new way to detect lensing. And it has been proposed that this would allow for new studies of astrophysics, cosmology, and fundamental physics, where some of the examples are on the right. And so these are essentially some of the reasons why we think that it's worthwhile to study gravitational wave lensing, and why we're doing these sort of studies now, as opposed to, let's say, 30 years later. And so with this, hopefully I'm motivated a little bit about why gravitational wave lensing is could be interesting to look into, and we can go into the actual search results. So the first LVC study on gravitational wave lensing. So what we did is we performed essentially a comprehensive study for kind of different aspects of gravitational wave lensing. So we started off with lensing statistics. So trying to essentially answer the question, do we expect to see gravitational wave lensing right now? And if we don't see gravitational wave lensing, what does it actually tell us? So what does it tell us about the, let's say, the population of binary black holes coming from high redshifts? And is there any way for us to constrain the rate of lensing? And this is something that informs the analysis. So, so essentially, this is an input that goes into the other analysis as well. And we also looked into lensing magnification. So essentially what happens when gravitational waves are magnified due to lensing. And there have been some suggestions in the published literature that maybe some of the high mass events that LIGO-Virgo is seeing could be magnified. And what would happen if they were is that this magnification could create these sort of high mass events that would actually be from intrinsically lower mass populations. So we investigated that aspect. And then we looked into strong lensing multiple images, which are these repeated events, and microlensing distortions, which create these sort of beating patterns. And so if we start off with the first, now that we have kind of the outline for the for most of the analysis that we did. So if we start with lensing statistics, what you can essentially do is you can essentially take the knowledge of the binary black hole population and the population of lenses and try to answer the question, do we see gravitational wave lensing? And if we don't see lensing, what does it actually inform us about the high mass, the high redshift population of binary black holes? And what we did here is we essentially took the current knowledge that we have of the binary black hole population. So it's illustrated here. It's the power law plus peak model from the latest population results. We took the population results and we tried to combine this with what we know about the lenses and the galaxy distribution in the electromagnetic band. And so we essentially modeled galaxies using the SDSS galaxy catalogue results and the galaxy clusters as lenses from the Tinker et al. Halo mass function. And
sorry, Otto, one question. Can you explain, because for non-experts, what's this power law plus peak model, if it's easy to?
Sure. Yeah, so the power law plus peak model is essentially one of the mass models that is used in the rate and population studies by the LVC. And so the basic idea is to have a power law profile fit with this peak function, so Gaussian peak, and it's fitting to the mass distribution of binary black holes. So it basically tries to answer the question, what is the distribution of black holes in the masses based on the LIGO-Virgo results. And there were several different models that were fitted, and right now the power law plus peak model is the one that shows the greatest evidence, and that's why we essentially picked this one. So it informs us about the mass distribution of binary black holes within the universe.
Perfect. Thank you.
Yeah, thanks for the question. And yeah, I forgot to mention in the beginning, but of course, yeah, if there's any questions, at any point during the talk, I'll be happy to elaborate on any of this further. Okay, and so if we now combine these two different populations, the population of binary black holes with the population of lenses that we expect in the universe, what we can do is we can try to model what is the rate or the fractional rate of strongly lensed gravitational waves, and they are summarized here in this table in the bottom right. And you can see that there are two different models, and the model is related to the redshift distribution of binary black holes. And the reason we have two different models is that the high redshift population of binary black holes is not very well constrained right now based on the LVC data. So what we understand quite well is what happens at lower redshift. But higher redshift, the current constraints are from the stochastic gravitational wave background, so the lack of a stochastic gravitational wave background. And so these observational results are in this B model. And the A model is a theoretically motivated model that comes from population synthesis codes. And you can see the fractional rate of lensing for double images and single images. So what that means essentially is that when you have strong lensing, you can have detection of one image or two images or more than two. And these are the fractional rate of lensing for galaxies, doubles, and galaxy clusters. And what you can see here is that the fractional rate at the current O3 sensitivity is very low. So this is roughly in the order of 1 in 1,000 to 1 in 10,000 events would be lensed according to these estimates. And so this is, of course, important information for us, because it also means that it raises to some degree against some of the recent claims that a significant fraction of the events would be lensed. And so these essentially tell us that, at current sensitivity, according to what we understand, the rate of lensing should be relatively small at the current sensitivity. What we also tried to answer as a question, or a question that we tried to answer within this study, is if we don't see strong lensing, so if there is no detection of strong lensing and there is no observations of strong lensing, what does it inform us about the merger rate density? So essentially the redshift distribution of binary black holes. And what it does is it mainly sets limits at the high redshift to essentially inform us that at high redshift, there shouldn't be that many mergers. So anything below this, above this, wouldn't be possible, because otherwise you would expect to see lens difference. And so this was the first analysis that we performed on strong lensing. But then we also looked into the stochastic gravitational wave background a little bit more. And the idea is to take the current estimates of the merger rate density, which is illustrated here, based on the local O3A RMP results and based on the stochastic results, to essentially model observationally what is the density of mergers within the universe at high redshift, and take these results to actually try to predict what is the fractional rate of either weak lensing or strong lensing. And we set constraints that based on these results, it should not be possible for us to see lensing at more than about 4 in 10,000 events. So these results are also essentially, to some degree, raising against some of the published results stating that a sizable fraction should be lensed. So this is another way to state that that in order for us to have a large number of lensed events, which was some of the claims in the literature, we would somehow need to explain these results. So the lensing statistic results based on the lack of a stochastic gravitational wave background. And so these were the statistical estimates that we performed.
Otto?
Yep.
Is this probability of all gravitational waves reaching the Earth, or only the ones that are detectable above some SNR threshold?
Yeah, they're only the ones that are detectable above a SNR of 8 that we used as a limit here. And we've also performed the same estimate with a couple of different SNR thresholds, and they're roughly the same. So it's not, yeah, so it's the fraction of detectable events.
Sure, and then, okay, if the detectors improve in the future, that's going to get much larger, or it could get much larger.
Yeah, and yeah, so these are all O3 sensitivity, and so if you go to higher sensitivities, then yes, the results will change. And that's an excellent question. It was actually one question that we already received before about this, specifically this graph. And yes, so it is the expected observable rate of lensing. Okay, and so then we can move on to the analysis of something that is closer to the actual data. So these were forecasts, but now we can move on to the actual events that we've seen. And the first study is lensing magnification. So essentially what happens when gravitational waves are lensed in either the weak lensing limit or in the strong lensing limit is that their amplitude can change. So that is illustrated here for a binary neutron star waveform, where the amplitude grows because of lensing magnification. And what happens then, because the amplitude grows, if you don't account for gravitational wave lensing, then our parameter estimation tools will inform us that this event came closer, that it originated from closer than it actually came from. So essentially, lensing magnification biases our estimates of the luminosity distance in a way that it appears to be closer to us than it truly is. And because it appears to be closer to us, it also appears to be more massive, intrinsically massive, an object. And so as a general result, what lensing magnification can do is it can create apparently high mass events within LIGO-Virgo. And this is also one of the reasons why there have been discussion about, possibly some of the events being lensed within LIGO-Virgo, because they were more massive than we had previously expected. And so what we did here is we actually analyzed these events, so some of the chosen events that were either within the mass gap or were surprisingly massive in other ways, and trying to answer the question, if they were lensed, what would be the lensing interpretation for these objects? And so we did that by assuming that they actually came from a lower mass binary black hole population. So for binary black holes, we expect that we assume that they come from below the mass gap, in fact, and they are lensed. And for binary neutron stars, that they came from the galactic double neutron star population.
Otto, by below the gap, you're referring to the very instability supernova gap, right?
Yes. Yeah.
Okay. Thanks.
Yeah. And we analyzed 5 events. So there was the 1904-25 event, which was a high mass binary neutron star event. There was 1904-26, 152-155, which is the NSPH event. And the reason that we investigated this event was because there was a GCN circular about the possibility that this could be a lensed binary neutron star, and so we included it in the analysis for that reason. And we also analyzed 3 binary black holes that had significant masses. And so what we found as a general result is that for the binary black holes under the Lensing interpretation, this would require moderate magnifications of the order of 10, and they would originate from roughly redshifts of 1 or 2. And for the binary neutron stars and NSPHs, they would require very high magnifications in order to explain them as lensed events. Overall, and I want to kind of emphasize this, is that we essentially didn't find compelling evidence of lensing magnification. We motivated that a little bit based on Occam's razor. And so this is based on the fact that we expect the relative rate of lensing to be very low. And so unless there is good reason to think that these events are lensed, so unless there's some kind of smoking gun signature for it, we have to conclude that they are not lensed based on Occam's razor. But nevertheless, the reason that this sort of study is important is that it allows us to characterize these events under the lensing hypothesis. And for example, if there are events that would require very high magnifications, then we might expect other different consequences for these events. So for example, if there is a magnification of 100 or more, we know that it's very close to the caustic. We know that it would need to be strongly lensed, most likely. And it may be possible to also have other signatures of lensing, like microlensing, that becomes prominent when you go to high magnifications. And so we essentially reported the intrinsic properties under this lensing hypothesis that can be used for follow-up studies. And so this was the lensing magnification study that essentially investigated some of these high mass events. And then we can move on to
Otto, one naive question.
Sure.
What is the magnification that one may expect to attribute to gravitational lensing without entering into the following conflict, that if you have a gravitational lensing, you have gravitational lensing for everything, also for whatever light is coming from that part of the sky? So maybe I have a scale problem in this reasoning, but I guess that you cannot assume whatever gravitational lensing magnification without entering into conflict with observations, other observations. Yeah,
exactly. And no, that is absolutely true. And so the conflict, I think, mainly for these events comes from the lensing statistical studies. It's a bit of a tricky question to answer, because technically it is always possible to some degree tune the merger rate density at high redshift, and if you tune it in a certain way, you can produce very high magnifications as well. And so I think there isn't. I would say it this way. So from our best understanding of lensing statistics, the best source for lensing would be a binary black hole at moderate magnifications from redshift of, let's say, 2 or 3, roughly. That would be kind of the prototypical binary black hole. But of course, that would mean that we, I mean, in order for us to kind of confirm that something is lensed, we would also need to have a smoking gun for it. So we would need to have, either find multiple images or some other type of signature that would actually confirm that this is a lensed event and not simply a high mass binary black hole I'm not sure if that answers the question. If not, I can go into more details as well.
Oh yeah, it's okay. It's okay. Thank you.
Yeah. Thanks for the.
I have another question, if I can.
Yeah.
So you mentioned here that you would require a given magnification to achieve some kind of alternative result that you're looking for. So my point is that once you assume that the event can be lensed, I guess there is a perfect degeneracy between the amount of lensing and the real source frame masses of the source. I guess you have an infinite range there you can play with. So when you say you would require higher magnifications than 100, is it to change the nature of the source? So for instance, to bring 190521 below the mass gap?
Oh, yes, yeah, exactly, yeah. So your understanding is correct. So if you take into account lensing, then by increasing the magnification, you can essentially, in a sense, reduce the mass of the binary. If you know what I mean. So essentially, if you correct for lensing, so if you up the magnification, then what you can do is you can debias the result so that it goes to below to smaller masses. And indeed here the requirement is that it goes towards to be consistent with the intrinsically lower mass population below the mass gap, for example, for binary black holes, and for binary neutron star or the NSBH to be consistent with the galactic double neutron star population that we observe in the EM.
Okay. Thank you.
Yeah, it's a very good question. Okay, so then I'll move on to the search for multiple images. And so there is a bit of a difference when it comes to magnification and multiple images, because for multiple images, there are fairly robust ways to search for them. And just to explain kind of what happens when we have multiple images within the gravitational wave band, the same essentially as what happens with electromagnetic lensing. So you can have images. If you had a telescope, you should be able to see something like this. There would be a binary black hole here, binary black hole here. And you would have essentially these sort of repeated events appear within the detector, so 1 and 2. And because they come from the same source, so you can see here in the illustration, it's the same binary black hole. The frequency evolution is the same. So the only difference between these two waveforms is the overall amplitude due to magnification by the lens, the arrival time here, because they travel through different trajectories at the same speed through different gravitational potentials, so they arrive at a different time. And this overall Morse phase, which comes from the fact that the lens can invert the images along one or two of the principal axes. And so, but otherwise, these are identical events that come from effectively the same sky localization. And so, if you can show that that you have two events that come from the same sky location that have identical properties within detector accuracy, then this would be essentially a lens candidate. So you search for repeated events. And so that's what we did. We essentially did 3 different searches for these sort of multiple images. So the first one, we asked the question, are there any event pairs within the gravitational wave detector? So the published, GWTC2 events, where we expect to have 2 events coming from the same sky location that have the same detector frame parameters, because if they have the same frequency evolution, then you would expect also, for example, the chirp masses to be the same. And so what we did was a posterior overlap calculation for that. So we looked at the posteriors of different events and contrasted them with one another. And we quantified the likelihood that they are lensed based on this overlap base factor. That quantifies how much overlap is there between these events. And then we also looked at lensing statistics to say, if we have 2 events with certain time delay, then lensing should produce typically time delays for galaxies between minutes to weeks to maybe a month, and for galaxy clusters a little bit longer. And contrast that with the unlensed expectation that they come from a random Poissonian process. And so you can see the results here. This is the overlap base factor, or the ranking statistic, as we've started calling it. And this is the ranking statistic based on the time delay, or the difference in the arrival time. And these are different events that we've seen within the GWTC2. And all of these are below 2 sigma. And so based on this analysis, we didn't conclude that any of these are lensed. But we also recognize that there are certain limitations to doing a posterior overlap analysis. So the first limitation is that because we're looking at posteriors, we can't go to arbitrary dimension, which basically reduces the efficiency of these searches. And so what we did is we also took 19 of the most promising candidate pairs, and we followed up on these with a joint parameter estimation tool, where instead of looking at the posteriors individually of the from the event pairs, we jointly analyze them. So we essentially do a joint parameter estimation where both of the pairs are analyzed simultaneously. And so the results from this joint parameter estimation are here for the 19 pairs. And just to explain what are these different columns, we essentially reported the coherence ratio first. And there was something very interesting that we discovered in here in these results, which is that if you look at the coherence ratio, which is essentially the evidence of the lensing hypothesis versus the unlensed hypothesis for an arbitrary prior, what you can see is that some of these values are really high. So some of the coherence ratios, which essentially describe the parameter overlap between two events, is quite high. These are log 10 coherence ratio values, and this is log 10 of 4.5, 4.9, 5.5, and so this was quite surprising to us at first, because we realized that there are actually events that have very high consistency in their parameters. They look very similar within the detector accuracy, which is what you would expect from lensing. But as it turns out, what we're really asking as a question when we look for strongly lensed image pairs is, what is the likelihood that a random two gravitational wave events produce something similar or something mimicking lensing by chance versus that they are actually lensed? And because of this, it turns out that our information about the binary black hole population, so their masses and spins, becomes very important. And we hadn't included this in the coherence ratio. Coherence ratio is essentially using mock priors, but we included them in the second column using Hanabi results. And you can see that these previous coherence ratios, they've gone down very significantly. So even though there was high parameter overlap, once you include the binary black hole and the lens population, according to the O3A results, the significance of these events went down significantly. And then we also included finally the selection effects. So the essentially the information that some, for example, sky localizations are more likely than others due to selection. And so finally, if you look at the last column, these are essentially the base factors that tell us and inform us about how likely are these lensed versus that they are not lensed. And you can see that they're all negative. And so overall, we found no evidence of strongly lensed superthreshold pairs within this analysis.
Can I just to check if I understand this? So you first look at pairs of events and you check how similar the two sets of parameters you're inferring is.
Yeah.
But then you say, given, so what I'm thinking about is that given that most of what we detect is in the same mass range and with the same spins and everything, then the fact that two of these pairs coincide is not very significant, because that can happen because of I mean, we basically tend to observe the same all the time.
Yeah.
So you're basically telling me that if for some reason we suddenly had a search algorithm or something that can start to detect high mass ratio stuff, or just increasing the family of observations we have, then these significances would rise actually, because the probability of random coincidence would be quite lower.
Yes. Yeah, absolutely.
Okay.
And yeah, that's a good point. And so yeah, I mean, it's the same also with increasing detector sensitivity. So if you get better, if you can better resolve the waveforms and their differences, then of course the significance also goes up. But you're absolutely right. And so the more information you include there, the smaller the chance of a random coincidence is. And that's why these population priors and the understanding of the underlying population of binary black holes is so important for these searches.
Okay. So if for some reason we suddenly detect, so we had 100 observations that look like what we have right now, and for some reason 2 of those happen to be a mass ratio of 7, which we have known as of now, then there will be a high probability of lensing for those 2 mass ratio 7 candidates, I guess. Okay, thanks.
Yeah. And I mean, I also want to mention that the lensing statistics also plays a role to some degree. So for example, what we need is, in order for us to detect lensing, we need to have access to fairly high, a fairly large detector horizon, because most of the lensed events come from redshifts of 2, 3, roughly. I mean, they're going to be magnified, but from a lensing statistics perspective, high mass events are always favored as a lensed event as well. And so these sort of considerations also go into these analyses.
Okay, thanks a lot.
Yeah, it's a very good question. And so these are the results that we did for the super threshold test. So we started off with the posterior overlap analysis, did joint parameter estimation. We didn't find good evidence of strongly lensed events. But then there is a third possibility, which is that what if some of these broad-based template bank searches that we do didn't identify the multi-image or the multiple image within the data. So we're talking about a situation where there actually is strong lensing, where we detected one of the images, but one of the other images is buried in noise. So the significance is not large enough that we can detect it with these standard templated searches. Then there is a third option, which is to try to do a targeted sub-threshold search, where essentially we would use these confirmed gravitational waves to essentially answer the question, what if, for example, for 190521, what if there is in fact a multiple image, but it's buried in noise? Then what we can use as a assumption when we do a template bank is that whatever multiple image that we're looking for, it has to be very similar to the 190521 or the confirmed gravitational wave detection. And so we did 2 different template bank approaches, so targeted searches, where in one we took the confirmed gravitational wave detection, took the posterior samples and used those to create the targeted template bank, and another one where essentially the maximum posterior sample was used as a single template approach to search for these sub-threshold lensed images. And so did we find anything? We essentially as a result, we discovered that there were 8 new triggers with FAR of less than 1 in 16 with this targeted bank. And we followed up on 6 of them with this joint parameter estimation tool. And overall, you can see again that there is a fairly high coherence ratio for some of these events. But overall, we couldn't find significant evidence of lensing. We performed also this population-weighted base factor computation on the most significant one, finding that it went to essentially negative values. And these are the search results with targeted template bank. And so even with this, we couldn't find any good evidence of strong lensing within the data. The last search that we did, and this is moving now from multiple images to microlensing, we essentially performed a search for the sort of microlensing beating patterns that you can see here. So this would be an unlensed waveform. And then if there is microlensing, so if the gravitational wave travels near a smaller lens, like a star or a compact object like a black hole, then it can induce these sort of beating patterns on the signal. And they originate from two effects. So the first effect is that when we go to smaller lens sizes, then the arrival times are no longer 1 week, they can be milliseconds. And so you would have multiple images combining at the detector that form these sort of superposition and cause these beating patterns. And another effect is so-called wave optics effects. And they arise from the fact that gravitational waves have very large wavelengths, and they can also couple to the microlensing background in such a way that wave diffraction takes place, and you have these additional beating patterns. And so we searched for these sort of microlensing effects using the isolated point mass lens approximation. And the results are summarized here on the right. These are different events. The violin plot shows the inferred redshifted lens mass, and the parallel axis shows the base factor in favor of microlensing. You can see that all of the base factors are relatively low, and so we couldn't find good evidence of microlensing in these searches. And so these were all of the results for this study. Essentially, we started off with statistical forecasts that were constraining the rate of lensing and the merger rate density at high redshift. We analyzed some of the high mass events under the hypothesis that they might be lensed. And we also did 3 different searches for multiple images from strong lensing. So we started off with posterior overlap, identified 19 possible candidates, passed it on to joint parameter estimation for follow-up, finding no good evidence of lensing. And then finally, we also did a sub-threshold search for possible triggers that would be below the noise threshold. And then also performed a search for microlensing induced beating patterns. So as a analysis, this is the first LVC analysis that is on a topic that is expected to be pursued further with new data. And so it's essentially a new topic for the collaboration that we're exploring for the first time. And to end the presentation on a positive note, what we expect is that when the current gravitational wave detector network expands, once more detectors come online and the sensitivity increases, our chances to actually detect lensing will also improve. And so with that, I'd like to thank you for your attention. And if you have any questions, I'd also be happy to take it now. You can also see the table of content on the right, but if you have, if you have questions about gravitational lensing in general or gravitational wave lensing, from content that is kind of beyond the search results or the content that was presented here, I'd also be happy to take those questions and kind of elaborate more. So thank you.